this circuit is a combination series parallel circuit with a resistor in parallel with an inductor and a capacitor in series. This is 5 volts, and this is 370 hertz. Then I have an inductor in series with a capacitor. This capacitor is 1 microfarad. The inductor is 100 millihenries, and my resistor is 1.2 kiloohms. So what I need to do is fill in the table of voltages, currents, and impedance. So first I'm going to find the reactances. So XL is equal to 2 pi FL. XL is equal to 2 pi times 370 times 1 e to the minus 6 farads. XL. Oh, I plugged in the wrong thing there. I'm looking for L. So L is 100 e to the minus 3 henries. So XL is 232.5 ohms. And XL is 90 degrees. XC is equal to 2 pi FC, 1 over that, and then XC is equal to 2 pi 370 hertz and 1 e to the minus 6 farads. So XC is equal to 430 ohms. This is minus 90 degrees. So thinking about my triangle, this is my XL. XL, and my XC is bigger. So that means I'm going to have a net. This is going to be XL minus XC. It's going to be negative. So XL minus XC is equal to 197.5 ohms, and it's in the negative 90 degree direction. Okay, so I'm going to start with my table. Okay, so this is going to be my voltage. This is going to be my current. This is going to be my impedance in ohms. This is my inductive reactance. This is my capacitive reactance. And this is the combination of the two. This is my resistor. And this is my total, or Z. Okay, so filling in my values here. So I've got 232.5, and this is in the 90 degree direction. This is 430. This is negative 90 degrees. This one is 197.5 in the negative 90 degree direction. This is 1200 and 0 degrees. And I know for redrawing this circuit, I have a resistor in parallel with, I'm going to call it a capacitor because it's more capacitive points down than inductive. So we're going to just call this XLC. It's the equivalent reactance. And so I know this is going to be 5 volts, 0 degrees. This is 5 volts, 0 degrees, and this is 5 volts, 0 degrees. And that's because the voltage drop from here to here is the same as the voltage drop from here to here, and that's the voltage drop of my source. So what I'm doing here is I'm going to find let's find I of LC. So we'll call this one 1. And so what I'm going to say is that is going to be my voltage divided by my Z. So that's going to be 5 volts and 0 degrees divided by 197.5 ohms and negative 90 degrees, which is going to be 25.3 milliamps and the positive 90 degree direction. So 25.3 and 90 degrees. I of R is going to be E over R. So this is going to be, let's just correct this. This is going to be X LC. So this is going to be 5 volts and 0 degrees divided by 1200 ohms and 0 degrees. And so that's equal to 4.2 milliamps and 0 degrees. So 4.2 and 0 degrees. So to calculate the current total, we're going to use our phasor diagram for current. So this is going to be my ILC, it's going to be my IR, and this is my I total. So I total is going to be ILC squared plus IR squared, square root. So that's going to equal 25.6 milliamps. So this is 25, and we have to find the angle. So the angle is theta is going to equal tan inverse of ILC over IR. And we plug those values in, we get theta is equal to 80.6 degrees. So this is going to be 80.6. And if we want to find Z total, so Z total is going to be the voltage over the impedance, or the voltage over the current total. And so that's going to equal 195 ohms. And so I'm just taking this 5 volts divided by 25.6, and then I'm saying 0 minus 80.6, and so that's going to be a negative 80.6 degrees. So 195 and negative 80.6 degrees.